such evaluations, and that will carry 20% of your marks. Okay, so out of this tutorial, though I'm not very sure, out of this tutorial we will see if we can design some kind of numerical coding problem or something like that. Okay, a numerical, I mean, where you might need to write a small code or something. We will look into that, but not very sure at this point. Okay, because most of the questions that we have is analytical kind of question, right? There are not many numerical questions at this stage. Okay, so this is the basic operational part of the course. So anyone has any questions? Okay, so one more thing that I forgot, I missed saying, is that I will be taking attendance just for the sake of record, not for this class, but from the next class onward, because this class I am finding it difficult to even show the slides, but from next class onward I think it will be more comfortable, and I will be taking attendance, which is going to be for the record, though there would be no weightage attached to it, because probably you can realize that you can enter and then read the newspaper or whatever. So we will not attach any weightage to attendance, though it would be recorded. So the transcripts of this recording, I guess, is going to be there in the chat link. So those who can't connect because of issues can always look into those chat links. But the chat links will be provided a day later, I guess. Okay. So that's all from the logistics of the course. So any questions here? Okay.
Ma'am?
Yeah.
Ma'am? Yeah.
Yeah.
Ma'am, you were saying something about the tutorial, the evaluation and all. I didn't get that part exactly. Like, it will be done once in a month or how?
No. So there are two ways of two sets of evaluation, right? One is the quizzes, which is going to happen one in every week. Okay, for like half an hour. So which will be evaluated right then, within a day or so.
Yeah.
Okay, so there would be 8 set of such quizzes. We will take best 5 of those 8 quizzes, and that will comprise the major 80% of your marks. And there would be tutorials as well, which you can take your time, which is kind of a homework, which you can take your time, solve it at home, and then the Moodle link will be open throughout. You can submit it in the Moodle whenever you wish to.
Okay.
Okay, so this tutorials will be graded. Say, so in a week you will do, in a month you will do about 4 tutorials.
Yeah.
So this 4 tutorials will be graded by the TA only once in a month.
Okay. Okay.
So we have 2 months, so approximately 2 such sets of tutorials. So each set will have around 4 tutorials.
Okay.
Okay, so this will carry 20% of the weightage.
Okay.
Okay, fine.
Yeah. Yeah.
Yeah,
Fine.
yeah. So let me move into any other questions. So anyone has any connectivity issues? No, I guess so. Even if they have, they cannot see. Fine. So so please write to my email, the email ID that I have given, if you have any query, whichever way. Another important thing is that who is the CR of the class? Who is the class representative? For third year, is he
Pranav,
right?
Pranav.
So Pranav Teja, I guess he wrote to me yesterday. So Pranav, what you need to do is you need to send me an email with your mobile number. So in case I have to do some last minute cancellation and I'm not online, then I might inform you to inform the other students. Okay, so please send me your mobile number. I will also share my mobile number with you. Okay, so
Okay, ma'am.
that's all from the logistic part. Let me move into the, so what we will do today is we will uh, give an introduction to aircraft structure. So it will take like 1.5 hours, and then I will move into the real business. But I hope I get a smooth transition. So I have to show another set of slides. I hope I get a smooth transition. Can you see the new slides?
Yes, ma'am.
Yeah.
Yes, ma'am.
So yeah, fine. So
Yes.
let me. Good. So this time it was easier. Okay. So let me. Am I clearly audible?
Yes, ma'am. Very
Yes,
clear.
ma'am.
Yeah. Okay. Okay. Fine. So let me go into the basic of the basic introduction to aircraft structure. Okay. So there I have. I mean, just for the sake of acknowledgement, I have taken several pictures from these two books. So due credit is given to those sources. Okay, so I always try to start the lecture on aircraft structure with a bit history of aircraft structure and to see how it has evolved over time, which of course it's interesting to know at one hand, and it is also important to see at how understanding of simple mechanics and simple structural analysis has gone a long way to help to make people fly. Okay, so this is a news clipping. So before the final flight by Wright brother, there have been, of course, I guess all of you all know, there have been a series of effort. Most of them were unsuccessful, but as we say, I mean, we always stand on the shoulders of giants. So there have been a lot of experience and learning from all those failures. Okay, so there was a person called Samuel Langley, who was a pioneer uh, one of the pioneer in aircraft before Wright brothers. So he was an American who were working on this on flights. So and there was a huge government funding supporting his research. So his demonstration flight actually failed miserably, and that led to a huge um, uproar in the government, in the congressmen, as well as the media. Okay, so this news clipping was published in New York Times in October 1903, where they said that the flying machine, which could actually fly, might take more than a million to 10 million years. Okay, if all the mathematician and mechanics guys put their brains together. Okay, but Wright brothers used to maintain their diary, and it was said that in 1903, October 9. So it's written in their diary that they started unpacking to build the aircraft on October 9, the same day when New York Times reported. And all of you all might be knowing that the first flight happened in December 17, 1903. So within 2 months, they could actually fly, okay, nullifying all the claims made by the newspapers and the government people. Okay, so as I go through the lectures, you will see that the Wright brothers and also the other people who have contributed a lot to flight had a very clear, apart from all other aspects of flying, all other aspects of aircraft, which are also very major aspects, they also had a very clear understanding of mechanics and structures. Okay, so before I go to this, this is kind of what the entire assembled aircraft structure look. Okay, this is the airframe kind of. You can see how complicated this is. Okay, and the obvious question that student struggle with is that, I mean, you will see as we go through the course, we will deal with simple beams. Okay, and the obvious question that students have in mind is that why am I studying beams when I have to deal with the structure as complicated as this? Okay, so there are two answers to this question. The first answer is that if you don't understand beams, if you don't understand the building blocks, you will never be able to design the structures of an aircraft. So no aircraft structural engineer sitting at Boeing or Airbus have has skipped their aerospace structural analysis course. Okay, so these are the building blocks. If you don't understand beam, you will not be able to understand what goes even further. Okay. Number one, that's the first question. The second question is that you will slowly realize that most important components of the aircraft structure are beam-like structure. Okay, they are slender, one-dimensional kind of structure and are best represented as a beam. Apart from the beam, there are always cells and plates like structure, but major load carrying components are beam like structure. So it's kind of understanding beams well helps you in understanding and designing most of the structure, aircraft structure, in a very efficient way. Okay, so this is a picture that I have taken from one of the books, which shows that a Boeing 7767 has 3.1 million interconnected parts with 85 miles of vary. Okay, and this parts are supplied by 1,300 vendors. So I mean, even a small vendor in some gully of Kolkata is also supplying parts to Boeing maybe. Okay, so you have to understand the wide range of material, the wide range of manufacturing and craftsmanship that goes into forming an aircraft structure. So that is one thing that keeps aside make aircraft structure so more complicated and so more intriguing than any other civil or mechanical structure. So what are the design requirements? What do I need to know when I'm trying to design an aircraft structure? The first is load requirement. Okay, so this information will come from the other streams of an aircraft. So you need, from the aerodynamics guys, you need to know how much load is going to come on that, how much aerodynamic load is going to come on the structure. Okay, what are the regimes of the flight? Okay, what are the speed? What are the operating altitudes of the flight. That is going to give you the aerodynamic load that is going to come. You also need to know from the propulsion guide that what is the engine thrust that this aircraft is going to experience, and that is also an important part in designing the aircraft structure. Similarly, from the flight mechanics people or the control people, you need to know the maneuvers that this flight is going to undertake, and that also is important to understand the load factor, the G that is acting on the flight. Have you all studied load factor? Let me just understand this. Have you all studied load factor? Are you all there with me?
Yes, yes.
Have you studied load factor?
We have studied load factor
We haven't.
explicitly in previous courses.
Pardon?
We haven't studied load factors specifically, means we might have studied the concept, but we haven't, like, may have studied the concept, but we don't know exactly what is load
Okay,
factor.
fine. So, but you know the G load and you know the weight, you know the definition of load factor, right?
I think
Okay, we will look into that later. Okay, fine. Anyhow, probably you will be able to appreciate that. I mean, the load that a structural engineer has to work with has to come from other operational aspects of the aircraft. Okay. So the second thing that you need to understand to do the design of an aircraft is to see how the structure is shaped. That is going to come from mostly from the aerodynamics perspective. Okay, the shape of the wing, the shape of the fuselage, which is primarily designed from the aerodynamic point of view, is another important factor in the structural analysis. So the structural analysis will depend on how the aircraft is shaped, how the wing is shaped. Okay, that's the second part. The third is the description of the environment where the structure will operate. Okay, you need to know what are the altitudes, what are the region where this aircraft, what are the region where this aircraft is going to operate. If it is working in extreme, most of the time, if it is working in extreme higher temperature, the material that you need to choose has to be done accordingly. Okay, if it is a navy aircraft, you have to probably take into account that there would be a lot of moisture involvement, and your material should be designed according to the considering the moisture that this aircraft is going to encounter. Okay, the other important factor, which is not so important for other kind of structure, is the description of interfaces. As you have seen in the last slide, there are lots of interfaces and connection between the components of an aircraft. Okay, and this also becomes an important aspect while we design the structure of the aircraft. You will probably be able to appreciate that each interface that you make, each joint that you make actually creates a region of vulnerability in the structure. Okay, each welding that you make, each fixture that you make is a point of lower strength or a vulnerable point in the structure. So that is also an important aspect when you design an aircraft structure. So now you have to tell me, so you are already in the third year, so you have to tell me what makes an aircraft structure different from other structures. So why don't we have a generic course on theory of elasticity? Why don't we have a generic course on computational mechanics? And can get away with it. Why do we have a special course on aircraft structure? So what do you think that makes an aerospace structure different from other structure? Anyone?
Ma'am, the boundary conditions of the aerospace structures are different from other structures. The aerospace structures need to be lightweight, and
Okay, lightweight is
they are
one point.
undergoing more. Yeah, they will be undergoing more forces than the other structures which are on the ground. Like the not only the ground forces impact the like atmosphere also impacts the structures, and like the aerospace structures need to undergo through rapid changes in the environment, and some.
So I buy your first point that they have to be light. I buy your third point that there is a lot of changes in the environment. Okay, but I don't buy your second point where you say that the loads are much higher than other structure. I mean, of course, there are like these windmills, right? They undergo huge. You must have seen those wind turbines, those huge windmills. They undergo a much more higher aerodynamic force than probably an aircraft. Okay, so I of course buy the first and third point. Anything else?
Ma'am,
Mm-hmm.
other structures on the ground are somewhat fixed to the ground, but aerospace structures will not be fixed to the ground.
Yes,
Like
yes,
buildings
but
and all,
see,
they have the one
I
fixed
just,
and like
I know, I know. See, but the implications of that comes on your flight mechanics and control, not on structures. Right? Are you getting my point? This boundary condition that someone was saying that a bridge or a building or even a windmill is kind of has a foundation on ground, so it has a fixed boundary condition, whereas aircraft is kind of a free boundary condition. But the implication of that comes on flight mechanics, where it is kind of a rigid body mode. A whole body is kind of moving, having rigid body kind of. You have done a course on flight mechanics? Have you all done a course on flight mechanics yet?
And we have it this semester.
You have it this semester. Okay, fine. So fine. So anyone else want to answer the question? Why is the aircraft structure so different? Okay, so I will kind of summarize what some of you all have said and just try to give it in a bullet form. So the first is lightweight. Okay, let me talk about this. Weight is everywhere weight is a concern, right? You would always like to build a bridge which has the strength that is required but is lightweight, because lightweight means less material. Less material means low cost. Okay, all of us are worried about money, right? Money is of course a very important factor. So weight is an important factor for almost all structure. You would like to make a building with minimum amount of material, okay, and which will reduce the cost. But for aircraft structure, it is an overriding criteria. It's an overriding criteria. I mean, at every stages of design, there has to be a person, an aircraft designer, who has to keep a check on the weight. Okay, which is not the case in other structure, not the case in civil structure or mechanical structure. For aircraft structure, weight is the primary constraint, the primary overriding factor. So there is no performance of the aircraft, excuse me, there is no performance of the aircraft which is degraded by an increase in the weight. Okay, so I mean, weight is also associated with the fuel consumption of the aircraft. So for no other structure, possibly weight is a overriding factor. Okay, it has to be lightweight. And to make it lightweight, there are two things that make aircraft structure lightweight. One is the material. We always try to find out a high strength to weight ratio material like aluminium. Okay. Recently, titanium and composites are also coming into picture. The second way that we make the structure lightweight is the geometry of the structure. We get into something called the thin wall structure. Okay, you will probably be able to appreciate this as we go into the course further. The geometry of an aircraft structure is made in such a way which is called the thin wall structure. Okay, this typical geometry makes the aircraft structure much more lighter than a civil structure. And as we make the structure thin wall structure, the analysis of the structure, okay, the theory behind the structure also becomes a bit different from the normal civil structure or mechanical structure. The second point is that that's one of the student has said that it experiences a wide variety of load. Okay, the kind of load that the aircraft is experiencing when it is taxiing or when it is in the ground is much different from the kind of load the aircraft is experiencing while it is in flight, in full flight. Okay, and also the kind of load the wing is going to experience in different forms of maneuver is also very different, and the class of load is entirely different. In, like, I will tell you, when it is taking off, the wing experience a vibratory kind of load, okay, a cyclic kind of load, oscillatory kind of load, but that might not be the case when it is in the full flight. Okay, so this change in the mode of loading, somewhere it is oscillatory, somewhere it is non-oscillatory, somewhere it is an impact kind of load. So when it touches down, the landing gear actually experience a thud or an impact kind of load. Okay, and analysis or designing a structure for an impact kind of load is a different ball game altogether. Okay, so this part you have to appreciate. This is not experienced in any other form of, in most of the other form of structure. This wide variation in the types of load. The third point is that it operates in extreme environment. There is a wide range of temperature. I missed saying moisture. There is a wide range of temperature and moisture over where an aircraft perform. Okay, while it is in ground, it is at the ambient temperature, say 25-30 degrees Celsius. But when it is in the full flight, it is at a very low temperature. Okay, and the structure enclosing the engine is at a very high temperature. So you should be able to appreciate the wide environmental parameters under which an aircraft perform, under which the material, the aircraft structure has to perform. Okay, this also makes an aircraft structure much more unique and much more difficult to analyze as compared to other structure. Okay, so if you have got a thorough knowledge in aircraft structure, you will see that all other mechanics is pretty simple. It's pretty easy as 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 compared to the aircraft structural analysis. Okay, that's what gives us an edge. I have seen many of the aerospace engineering students graduate and they do high level mechanics, high level structural analysis with much ease as compared to the other disciplines like civil, mechanical, who also does structural analysis, but not as complicated as we deal with. So that is one one important aspects of aircraft structure. So you should feel lucky that if you master aircraft structure, you will be a boss. I mean, you will be a boss of structural analysis. You can do structure and analysis of any other discipline with much more ease and much more finesse. Okay. So let us go into a bit history of aircraft structure. Okay, to understand. So any questions? Any questions? Yeah. At least one of you should respond. Otherwise, I'm not even sure whether I'm connected.
No questions, I think, ma'am.
No questions, right? Okay. So anything that one wants to add? No, right? Okay. So let us get into a bit history of aircraft structure, and you will see how it has evolved from very simple truss analysis to a very complex analysis that you do now. So Octave Canute in between 1832 and 1910 is called the father of aircraft structure. So he was a civil engineer who was with railways and is acclaimed for many fantastic bridge designs that he had done for railways. Okay, so after he retired from railways, he took a keen interest in making flying machine, non-powered flying machine. Okay, there was no power. So what he started with is a biplane where he had simple truss structure. You all of you all have studied truss in your first year mechanics. Okay. So you know what a truss is and you know how to analyze a truss. And you probably also know how simple it is to analyze the truss. Okay. Because it's simple, so it is taught in the first year. So it's a very simple thing, that very easy thing, very, what should I say, very easy to visualize thing. Okay, so the first aircraft structure that was built was a biplane having a two force member truss, which was just wrapped with a linen or a cloth kind of material, and it actually performed well as a glider from structure's perspective. Okay, next was so in between there were a lot of improvement that was done on aircraft from on the aircraft structures context. One person that comes should be mentioned is Samuel Langley. I said whose flight was a failure. Okay, but he actually did a lot of improvement on developing the aircraft structure. So this is the design, the airframe, if you can call it so, of Wright brother. Okay, this was a simple two force member truss, a biplane that was built by Wright brothers in March 1903. Okay, so the book where I got this picture from, I mean, you would like to see how simple it is. I mean, yet it was very successful, very efficient. Okay, so the book that I got this from also has a portion of their patent that they have filed in 1903. So see, Wright brothers, they understood the mechanics so well that see, they had this truss-like structure, right, which actually made the spars, bows, and ribs. Okay, the best part of this truss kind of structure is that if any part of the truss structure was damaged, they could actually replace only that member. Okay, and instead of replacing the entire structure, they could just replace the single member that was damaged. That was one more advantage of using a truss structure. So coming back to the understanding of mechanics of the Wright brothers, they had wrapped the linen or cloth in such a way that the fibers of the cloth were aligned 45 degree plus minus 45 degree. So I will show. So these are the ribs, and they had actually aligned the fibers of the linen in plus minus 45 degree. Okay, so can someone tell me why was this done? So the ribs are there. Say they are at 0 degree. They are at 0 degree and 90 degree. And Wright brothers made a point that the fibers of the linen are aligned at plus minus 45 degree. Anyone can tell me why was this done?
For vortex generation, maybe.
For sorry.
For vortex generation, so that the
No, from structure's perspective.
Ma'am,
Structure's
if
perspective.
the truss is bent, then the fabric can easily stretch.
to make the wings stronger.
No, there is another reason for making it plus minus 45. The fibers. Keep in mind the fibers. What is the fiber? The fibers are most trendier part of the cloth or linen. Anyone else? Someone was saying something. So these are the spars
Even
and
though
ribs.
the
Yeah.
even though the if the ribs break, the fibers will take the position of the ribs and like provide.
No, then I would make the fibers. Then I would make the fibers also in 0. So see, these are the ribs and spars, right? 0 and 90 degree. Say this is 0 degree. This is 90 degree. So if your logic is right, then I will also put the linen, say these dotted lines, these fibers also in 0 and 90 degree. So if they break, I will these fibers are going to take up their job. But they had put it in plus minus 45 degree, somewhat like this. Anyone from your first year mechanics? Anyone from the first year mechanics? Think.
And for symmetric load bearing.
No, you are missing something. What happens at 45 degree?
The maximum plane of shear.
Yes, exactly. So what's your name? Can I know your name?
I'm Kshitij.
Okay. So the thing is that, see, the structure is going to experience normal stresses as well as shear stresses. Okay, and the in-plane shear stresses generally happens at plus minus 45 degree. Okay, and this fiber being more capable of carrying more strength are aligned as plus minus 45 degrees, so as the in-plane shear stress is also taken care of. Okay, that's the sole purpose of putting them in. So here somewhere it is mentioned that it has so plus minus 45 degree with respect to the spars, okay, so that they could take the in-plane shear stresses. Okay, so then of course the next thing that happened is moving from a biplane to a monoplane so as to reduce the drag. So all of you all might be knowing that a biplane has much more drag as compared to a monoplane, and this was another milestone in aircraft structure, where a monoplane, the same thing, a truss covered by a cloth, but a monoplane, and it was supported by this wires which is connecting the wing with a post in the mid region of the wingspan or the fuselage. Okay, and this was in 1909, and this was a flight between Britain and France crossing the English Channel. Okay, and and following this, there have been several improvement in this truss kind of structure, but the next milestone came where in 1911, when a person called Louis Becquerel, he got rid of this truss kind of structure, okay, to further reduce the weight of the aircraft and introduce something which is called a monocoque structure. Okay, this is a very common terminology of aircraft structure, which is called a monocoque structure. So what does monocoque means? It's a Greek word again. So monocoque means single cell. The meaning of this, yeah, it's written. It is called single cell construction. Mono means single and coque means shell. So it's like a Coke can. Okay. So he used wooden layer, multiple layers of wood. He made the fuselage out of multiple layers of wood which were glued to each other and made a cylindrical shell-like structure, okay, which actually reduced the weight of the structure to a considerable extent. And with this monocoque fuselage, he could actually fly at 125 miles per hour. Before that, the maximum speed it could attain was around 60 miles per hour. Okay, and this monocoque structure became very common. Okay, for next 10-15 years, a lot of aircraft was designed with this monocoque structure. Okay, but this is an example of monocoque structure. So in 1912, a person called Deperdussin, okay, he had built a fuselage made out of 3 layers of wood reinforced with intermediate layers of fabric, okay, and this were of course expensive because you need high quality of wood, and the craftsmanship involved was also very sophisticated. Okay, now can someone tell me, but this monocoque structure was improvised in couple of years. Okay, so they didn't stick to this single shell kind of structure. They moved into something called semi monocoque structure. Now again, someone has to tell me from your previous course knowledge, what would be the issue with monocoque structure that people have discarded monocoque structure and moved into something called a semi monocoque structure. So have you all understood what is a monocoque structure? So you just imagine a Coke can. Okay, so the fuselage is like a Coke can where the what should I say, where the thickness of the can is much higher, okay, and that's all. There is no truss, so it's just this cell structure. Okay, previously there were trusses inside and the truss was wrapped with a linen. So he got rid of this truss structure, Becquerel, and made a single shell kind of structure called a monocoque structure. Okay, is this part understood? Do you understand which is a monocoque structure? It's a very commonly used terminology in aircraft structure. So you should be acquainted with it. It shouldn't happen that someone in interview asks you what's a monocoque structure and you are not being able to understand. So everyone has understood what is a monocoque structure? And now tell me, this monocoque structure stayed for around 5 to 10 years, and then people discarded it and moved into something called a semi-monocoque structure, an improvised version of monocoque structure. So someone can tell me why?
It is not very good at the formation
It is not very good at?
Deformation.
What kind of deformation?
Twisting.
Okay, so what will happen if you take a monocoque structure and twist it? Give a torsion. You are right. You are giving me the right answer. But just refine your answer a bit. So what will happen if you take a monocoque structure and twist it?
It will collapse easily.
So it is something will happen which is called buckling. Have you all studied buckling?
Yes.
Yes. So if you take a huge shell, just imagine a Coke can, right? If you take a Coke can and you give a twisting moment, it will deform largely. There would be a large deformation, which is called torsional buckling. Okay, the terminology for that is torsional buckling. But from a laymanish point of view, there would be a large deformation due to a small torsional load. Not only torsional load, imagine a Coke can and give a point load somewhere. Okay, give a compressive load somewhere. It will also buckle. It will also undergo a large deformation and a huge buckling. Okay, so as what's your name? Can I know your name? Who gave me this answer?
My name is Arnab.
Arnab?
Yes.
Okay, fine. So, this buckling or this large deformation is a big problem with monocoque structure. Now, what was happening with smaller aircraft? Okay, with a single-seater aircraft or two-seater aircraft, it was fine because the size of the fuselage was not too big. Okay, and monocoque was doing well. But with World War II, there was a huge increase in huge advancement in aircraft technology, and larger aircrafts were being attempted. Okay, at least four-seater aircraft. As the size of the aircraft increased, this monocoque structure was no longer safe from buckling or buckling deformation point of perspective, from buckling perspective. And what came is a semi-monocoque structure. So all the aircraft till date follow this semi-monocoque structure. What is semi-monocoque structure? The same shell kind of structure, okay, but with reinforcement, with longitudinal members, which are these stringers, okay, and transverse members, which are called the ribs or bulkheads. Okay, so this longitudinal stringers, okay, divides the monocoque structure into smaller components and therefore reduces the buckling of the structure even when the structure is large. Okay, and this kind of structure is called a monocoque structure. So when as I said, when the airplane size grew, the monocoque design was not suitable as they got buckled or got deformed. And reinforced or semi-monocoque structure came into picture, where the criteria of lightweight was still preserved, okay, but it was much more structurally stable. Okay? So all the aircraft structure that you see is a semi-monocoque structure. Okay, don't forget this terminology. Okay, this should stay with you. Any questions here? No. Okay, let me go into some examples of first examples of semi-monocoque structure. Since 1920s, major airplane structural component use semi-monocoque structure, which were thin-walled cells with internal stiffening member. The first was Junker F-13 passenger airplane, which was built in 1990. First flight was in 1919. So around 314 Junker airplanes were produced, okay, and it was in service with 60 airlines between 1919 to 1913. The other important advancement with Junker was not only it was a semi-monocoque structure, but also it used metal rather than wood. I will come to that later. Okay, so this kind of started the present day design, the present day semi-monocoque structure of aircraft. So we will talk about semi-monocoque structure hereafter. Okay, so let me get into the semi-monocoque structure. So any questions here? Anyone has a question? So I will upload the slides in Moodle. Okay, in case you have a question, in case you want to relook into the slides, and I guess the transcripts are also going to be there in the chat window. If you don't find it, let me know. So any questions here?
Yes, ma'am, I had it out.
Yeah.
Ma'am, when you were
Can
talking.
you tell your name, please?
Yes, ma'am, my name is Ritu.
Okay, Ritu, tell me.
So in the slide where you talked about how we have stringers to make it smaller parts, so we're reducing the bulking, buckling. Yeah. What is the bulkhead and the formers? I didn't understand.
So the stringers are longitudinal members. Okay, it is along the length of the fuselage or wings, and this bulkheads are lateral members. Okay, or transverse members. I have pictures of bulkheads. I will show you more elaborate pictures of bulkhead later. So these are lateral members which laterally divides the monocoque structure into parts. Okay, one is the longitudinal members, which is the stringers, and one are the transverse members, which are ribs and bulkheads, so it makes kind of a grid of the entire shell. Are you getting my point? It also, the main purpose of the bulkhead is not to reduce buckling, rather than the job of bulkhead is to maintain the shape of the fuselage, shape of the semi-monocoque structure or the wing. Okay, have I been able to answer your question?
Yes, ma'am. Yes, ma'am.
Yeah. Anyone else has a question? Okay.
And how exactly that it retains the shape of the structure?
I didn't
How exactly that part will retain the shape of the structure?
So see, the best way to visualize aircraft structure is a Coke can, right? So you just visualize a Coke can, which is a huge one, right? Because of the self weight, it will kind of get buckled and deform. Okay, so the stringers are longitudinal members which are maintaining the shape of the Coke can and preventing it from buckling when load is applied. Okay, even when load is not applied, if you imagine a huge Coke can, it will get deformed because of its own weight. Now this bulkhead or the ribs, sometimes they are called ribs also. I mean, there is another class of these lateral members which are called ribs, which it tries to maintain the shape. Right? It's just a reinforcement which prevents the Coke can, say, to collapse because of its own weight. Is it okay? Are you happy with the answer? Yeah. Okay. Okay. So this is a typical. Anyone else has a question? Okay. So this shows. Can you all see the pictures clearly?
Yes.
Yeah. Okay. So so this is a typical semi-monocoque structure. So this is a wing and this is a wing. I guess all of you all understand that. So this is a wing and this is a fuselage. Okay, so so what happens is that I don't know whether I have a, do I have a better structure, better picture? No, I don't. So I have to show it. Okay, so if you carefully look into the wing, so there is a skin which is the outer, which is the covering of the airframe. Okay, so the wing, the outer layer of the wing is called skin. I guess all of you all know that. Okay, so this is the skin, the outer layer. This is the skin. Okay, the skin. Okay, now if you look inside, there are these longitudinal members. I think you are being able to see that. These longitudinal members are called stringers. They are also called spars sometimes. They are a different name. I will come to that later. Okay, they are called stringer. Even in a fuselage, you can see the stringers, these longitudinal ones. Okay, they are called stringers. Okay, that actually I will come into the structural function of the stringers in detail later. Okay, first now understand which are the stringers. They are sometimes called spars also, not only stringer, they are also called spars. There is a slight difference between what is a stringer and what is a spar. We'll come to that later. But this longitudinal member can either be a stringer or a spar. Apart from the stringer, there are lateral member, transverse member. I don't know this ones. Okay, this ones. See, you can see something here. These are called ribs. Oh, spar is already mentioned here. So these are called ribs. This transverse member. So the counterpart in a fuselage, the counterpart of rib in a wing, in a fuselage is the bulkhead. Okay, bulkhead and formers. Sometimes people call it formers. Okay, those are the lateral or transverse member. Okay, so these are the typical structural component of an aircraft structure, be it a wing, be it a tail, or be it the fuselage. Okay, it mostly consists of a skin, the outer part. It consists of longitudinal members, which are stringers, spars. It consists of transverse members, which are called ribs in case of wing, and bulkheads or formers in case of fuselage. Okay, the three things that you have to keep in mind: the skin, the outer cover, the longitudinal member, stringers and spars, the transverse member, ribs or bulkheads. Okay, that's all. That's all that you have to deal with. Now, let me get into much more detail. Okay, this is a cross section of a wing. Any questions here?
Excuse me, ma'am.
Yeah.
Ma'am, I didn't quite understand how longitudinal and transverse is defined, because in the wing, the longitudinal member, the stringer, is perpendicular to the flow of air, whereas in the fuselage, it's along the direction of flow of air.
Okay. So this is the span of the wing, right?
Yes.
Okay, so the member aligned along the span of the wing, the lengthwise of the wing. If you don't want to remember span, the lengthwise the components in the lengthwise direction of the beam and the fuselage is the stringer or the longitudinal member. Is that okay?
Yes, ma'am.
Okay, and the members, which is 90° to the lengthwise direction, is the ribs, lateral member or transverse member, and they are ribs or bulkheads.
Okay.
Okay, so you don't if span and all is confusing it, just remember the length, the longer dimension of the wing, the longer dimension of the fuselage is the length.
Okay.
Okay, and the structure aligned to the length is the longitudinal member. Okay, so let me get into the much more details of the, see, this terminology, you probably have to remember it all your life, because it's a matter of disgrace if you can't answer a question on what is meant by spar, what is meant by stringer, longerons. Okay, these things has to be there with you. I mean, uh, you cannot be an aerospace engineer and not know what is a longeron or a stringer or a spar. Okay, so uh, so I think this wing cross section is visible. Okay, so wing, tail or other aerodynamic surface mostly have this structure. Spars are again longitudinal beams. Okay, so the beams, unlike the conventional beam, see, all these days mostly you have thought of beam as a rectangular cross section beam. Of course, in your first year mechanics, you have studied about I section. Oh, you are not being able to hear?
Ma'am, your audio is muted.
Am I audible?
Yes, ma'am.
Yes, ma'am.
So maybe we'll close the, since this is a
Ma'am, not audible.